Hello dear students, good evening everyone. So in the last class we were discussed here some of the most important concept, that is evidence for an Bohr's atomic model, and also discussed some of the important expressions based on this Bohr's atomic model as well. Okay, so guys, in this session we are going to discuss, or we are going to learn that how to solve some of the numericals based on that hydrogen spectrum, and as well as that some of the important expression what we were discussed in the previous session, isn't it? So based on those particular expressions we are going to solve some of the numericals today in this session, guys. Okay, so I have some of the numericals for you. Okay, so we'll discuss today one by one here. Okay guys, so let's focus on that here. Very first numericals based on that here, spectral lines means like hydrogen spectrum. Okay, most probably so you guys have for your syllabus number of numericals based on that frequency, based on that wavelength, and based on that hydrogen spectrum as well. Okay, so we'll discuss those particular numericals today. Okay, so let's take that very first numericals here. That is, the problem would be like that: in a hydrogen spectrum, if electron moves from a 7th orbit to 1st orbit by transition in multi-steps, okay, then find out the total number of lines in the spectrum. The thing is that, so what we are going to calculate, a particular electron that has made an here transition from here a 7th orbit to 1st orbit. So in this particular situation, so how many numbers of spectral line would we get? Okay, we are going to calculate that particular stuff there over. So the thing is that, let us assume that is the 1st orbit. Let us assume this is the 7th orbit. If an electron had made a jump from here 7th orbit to 1st orbit, so in this particular case, so how many spectral lines we are going to get, guys? Okay, so we are going to calculate that particular stuff here. So we'll solve that. So, and by the way, we are actually know about here a particular formula. Okay, so the total number of spectral lines. Okay, so we have that here. In order to calculate that here total number of spectral line, we have one particular certain formula. That formula could be like that: total number of spectral lines. Total number of spectral lines, which equals to N2 minus N1 into N2 minus N1 plus 1 divided by 2. So this is the actual formula, guys. So when we have to use this particular formula means, if they are going to ask here total number of spectral lines. Okay, when an electron had made and jumps from here a higher energy level to lower energy level, then how much of spectral line we are going to get in this particular situation. Okay, so right now we have a problem here, that is electron that has to be jumps from here 7th orbit to 1st orbit. Then that, so in this particular scenario we are going to calculate here how many spectral lines we are going to get here, guys. Okay, so this is the thing. So how to we are going to actually find out right now here N1 and as well as N2 value. So in this particular case, N1 value would be here, that is first means 1. N1 value will be first because lowest energy level, that's why that N1 value will be here 1, and N2 value, guys. So N2 value means electron that have been jumped from a higher energy level. Higher energy level in the sense 7th orbit, that's why that N2 value would be here 7. So these two value, let's substitute in this particular formula, and thereby making simplification, and ultimately we are going to get a proper answer for that. So we'll take over this particular numerical right now. So let's substitute, guys. N2 value is nothing but here given value, that is 7. I am going to substitute in here, and N1 value, guys, 1. Then again here N2 value 7 and N1 value 1. In that formula plus 1 is also there, divided by 2. So let's make it simplify, guys, right now. So the thing is that we are going to get here 7 minus 1 6, and here minus 1 plus 1 get cancelled, guys. So 7 will be remains here, and in the denominator 2 has to be there. Okay, let's simplification further. So 2 1s are 2 3s are. So ultimately the answer would be here 3 into 7, that is 21. So 21 will be the answer for your very first numericals. Okay, so when an electron made a jump from here 7th orbit to 1st orbit, then the total number of spectral line could be, that is 21. So this is the way of simplify these kind of problems, guys. Okay, so very simple. The question will be like that. I am just going to repeat one more time. How to focus on this particular question, guys. See, in a hydrogen spectrum, if an electron moves from here 7th orbit to 1st orbit by a transition in multi-steps, then find out the total number of lines in the spectrum. Okay, whenever he used to ask here total number of lines, means we are going to have a formula, that is this particular formula, guys. That is total number of spectral lines will be equal to n2 minus n1 into n2 minus n1 plus 1 divided by 2. We have to use this particular formula, thereby we are going to get an actual answer for such kind of questions. Okay, so this is all about here simplification of that first numericals. So let's go with that second, guys. So what will be the stuff we are going to get in this particular question? We'll see that the second question will be like that. In hydrogen atom, if electron moves from nth orbit to 1st orbit, okay, by transition in multi-steps, multi-steps. So multi-steps means that particular electron that has to be overcome here, that Fund series, Lyman series, Balmer series, each and every series, okay, in multi-steps, isn't it? In hydrogen atom, if electrons moves from here nth orbit to 1st orbit by transition in multi-steps, if there are total number of lines in spectrum are 10, if there are total number of spectrum are 10, okay, then find out value of n. Then actually what we are going to calculate here, that value of n, guys. Okay, see, in a hydrogen atom, if electron moves from here nth orbit, we don't know which particular orbit that is, so generally that is nth orbit. Okay, so to 1st orbit by a transition in multi-steps, So in this particular situation, and one data has to be given already, that is if there are total number of lines in spectrum are 10. So he has given one particular data, guys, that is total number of spectrum will be 10. So then what we are actually going to find? Then we have to find here that value of n. So we should find out here value of n, guys. So let's have that same formula. So in this particular formula, we are actually going to find out here n value. So let's see that how we are going to get that particular answer for this particular question. Okay, I am just going to write here again this particular formula, guys. See, the same formula, but you know that asking of question will be different. Okay, so based on that question, so what will be the method of simplification? We have to go with this particular manner. Okay, let's write down here total number of spectral lines which equals to n2 minus n1, n2 minus n1, n2 minus n1 plus 1 divided by 2. So in this numerical, one given term will be there, that is total number of spectral line. There is total number of spectral line, how much, guys? Total number of spectral lines. So total number of spectral lines, given value, that is take down, guys, that is 10. Okay, that is 10. Okay, so yes, and then n1 value, guys, that is 1, because that is given value, because electrons moves from here nth orbit to 1st orbit. So higher energy level to lower energy level, n1 stands for here lower energy level, that's why that value of n1 would be here first, means 1, have to take that 1 value, and let's put that value of this particular thing in this particular formula, that is total number of spectral line will be given, that is 10. I just have to write down 10 here. Okay, n2, so n2 is nothing but, guys, n2 is nothing but n, because electrons that have to be moves from here nth orbit, isn't it? Higher orbit, nothing but, that's why n2 value will be here n. Okay, I just have to take n minus n1 into n2 means n minus n1, n1 value will be here 1, and again n1 value will be here 1 plus 1 divided by 2. Guys, let's see that here minus 1 plus 1 get cancelled, isn't it? Okay, So 10 which equals to n minus 1 into n. Okay, and let's shift the 2 over here. Okay, then we are going to get 2 tens are 20 which equals to, so guys, let's simplify this particular term here. N into n square minus n into 1 minus 1. Okay, let's write in that equation form, then that n square minus n minus 20 which equals to 0. So we get one particular equation here, that is n square minus n minus 20. So we have to calculate right now n value. So guys, just look at here, this is nothing but quadratic equation, right? So we have to factorize this particular term right now. If you want to factorize means, so what will be the answer we are going to get here? Okay, so I have to write guys here, we'll see that. Okay, so let's factorize this particular equation. Then what we are going to get here? See guys, we have formula, that is total number of spectral lines which equals to n2 minus n1, n2 minus n1 plus 1 divided by 2, and that n2 value that has to be given nothing but nth orbit, means higher orbit, it will has to be taken as n, and n1 value will be here. So electron moves from here nth orbit to first orbit, means lowest energy, that's why n1 value will be here 1, that's why I have to take here in the place of n1 will be 1. Okay, and how to some of the values have to be substitute in this particular formula, and I am just making simplification guys, that's it. Okay, n square minus n minus 20, let's so factorize that particular equation, and we are going to get actually here n square minus 5n plus 4n minus 20. Guys, suppose if you are going to factorize that particular equations, means we are actually going to get this particular equation. 5 minus 4 1, so 5 4s are 20. So actually we are going to get that particular equation. In order to do that, so further simplification, if you can subtract these two terms, we are going to get this one original equation. Okay, so guys, let's concentrate these two terms. So in this particular term, what will be the common term here? N, right? So we have to take common as a n, and actually we are going to get here n minus 5 plus, so in this case, so 4 will be the common term, then that 4 n minus 4 5s are 20. Okay, then we are going to get here two particular value, that is n plus 4 will equals to 0, and n will n minus 5 which equals to 0. So here n value cannot be 0 guys, n value cannot be means negative. Okay, so that's why we couldn't take this particular value, but rather we have to taking here n minus 5 which equals to 0, then we are actually going to get here n value which equals to 5. Suppose if you simplify this one, n value is going to get here in that negative form. Okay, n value cannot be negative guys, so that's why, so we have to seek there or which particular n value having here in terms of positive term. Okay, so that's why here we are going to get n which equals to 5, this is that actual value for that n. So this is the right now answer we are going to get for this particular equation. Okay, so this particular numerical, so total number of lines in that spectrum are 10, and then find out that value of n. So ultimately what will be the value of n here? 5. Value of n will be here 5. Okay, so the thing is that guys, so I think I just have to write this particular equation here, because it would not be visible in this particular right now situation, just I have to write here itself. So guys, this particular this particular equation, if you are going to factorize, means we are going to get that equation in this particular form. Okay, so let's write that particular equation right now. N square minus 5n plus 4n minus 20 which equals to 0. Guys, if you simplify this particular equation, then we are going to get this particular form, n minus 5 plus 4 n minus 5. Okay, yes guys, let's take here n plus 4 and n minus 5 we are going to get here two particular form here. Yes, n plus 4 which equals to 0, n minus 5 which equals to 0. So, n which equals to minus 4 and n which equals to plus 5. So, actually we are going to get that value in terms of positive, because n cannot be negative, guys. Keep in your mind, n value cannot be negative. So, that's why, so we have to know here, we have to find out the value of n in terms of positive. So, that value we actually going to consider. Okay, so ultimately for this particular question, n value will be here 5. Yes, so guys, this is that simplification of this particular numericals. So let's take down. Okay, so once again I am going to repeating here. So the numerical will be like that: in hydrogen atom, if electrons moves from nth orbit to first orbit, okay, by transition in multi-steps, if there are total number of lines in spectrum are 10, then we have to find out here value of n. Okay, if an electron that has to be made and jumps from here nth orbit to first orbit, we don't know which particular orbit it was. Okay, so we are going to actually find out that particular value of n with this having these particular datas. Okay, and we have actually one particular formula for this particular numerical will be here: total number of spectral lines which equals to n2 minus n1 and n2 minus n1 plus 1 divided by 2. So in this numericals we have here a given data will be here total number of spectral line he has given already, that is 10. Okay, and how to make it simplify further by taking that n2 value as a n and n1 value as a 1. How to put that particular values in this particular equation, and let's go with that further further simplification, and ultimately we got this particular equation, guys. So let's factorize that particular equation, then we are going to get this particular form. And if you want to make that further simplification, ultimately we are going to get here two values. So among those two values, n can stands for here positive, we should consider that particular value, guys. Okay, so we shouldn't take here those particular values having here in that negative form. We couldn't take that one, so we have to take here that n value as a positive form. Okay, so this is the way of simplification of this particular numericals. So let's go with the third problem. So what will be there? So yes, guys, so we have actually that the third equation means third numericals here. So that numericals will be like that. So when yellow light emitted from a lamp as a wavelength that can be represented in terms of lambda, so of a 580 nanometer, calculate the frequency, means we should have to calculate here frequency and wave number of the yellow light. See guys, the thing is that he has already given a one particular data as in terms of wavelength. So we have to should use that particular parameter in order to calculate here wave number and as well as that frequency. Very simple. So the thing is that we have to know that a particular relationship between that here a velocity term and frequency term and as well as that wavelength term. So by doing this particular scenario, we are going to get a particular equation, thereby we are going to solve that this particular numericals, guys. Okay, so let's take that particular equation right now. Okay, so the first have to write that given data what he actually given there over. So a lambda will be here 580 nanometer. Okay, 580 nanometer, guys. So let's take that lambda has to be given, and we actually have to know here one particular equation, that is C which equals to nu lambda. Okay, suppose if you want to get an equation in terms of frequency and as well as that wavelength, because we have to calculate here right now frequency and wave number. So we have to actually going to get here two equations, guys. One will be for wave number. Wave number we have one formula, that is nu bar which equals to 1 by lambda, means wave number is nothing but here reciprocal of wavelength. And one more equation we are actually going to have right now, that is so nu which equals to C by lambda. Okay, so right now we are going to calculate here frequency. We have to calculate here frequency and wave number itself. Okay, so in order to find out these two particular parameter, we have to know here the two equation itself. Okay, one will be for that nu bar means wave number, and another one will be for here frequency. Okay, so we have two equation. So in order to making use of those two particular equation, then we are going to so calculate or simplify these particular numericals. So let's take that given values in this particular equation, that is lambda which equals to 580 nanometer. Right now guys, I am going to calculate here frequency. Okay, so what will be the answer we are going to get so by having that frequency here. So frequency has given, so frequency I have to find out, and wavelength has given that in that question also. Okay, so just take new, because I am going to calculate here frequency, and that guys, C value it has to be given, so it means it will be standard. Okay, that velocity of light, that is 3 into 10 to the power of 8 meter per second. Have to take that particular value also there over. So let's substitute these two particular value guys. C value, that is 3 into 10 to the power of 8 meter per second and divided by, so means wavelength value guys, wavelength value will be here 580 nanometer, means we also have to know here 1 nanometer value would be 10 to the power of minus 9 meter. Okay, 1 nanometer value will be here 10 to the power of minus 9 nanometer. So you have to take down, so lambda, that is 580 into 10 to the power of minus 9 meter. So in this case meter get cancelled, and if you want to simplify these two particular term means, so we are actually going to get here value would be here 51.724 into 10 to the power of 13 per second. Okay, so this is the value guys. Okay, actually this is the stuff here. So this is that way of finding out that here frequency. We are going to get ultimately here frequency, and we actually have to calculate right now, that is nu bar. So we have to calculate here nu bar. Okay, I just have to write there over guys. Okay, let's be concentrate on this board. Okay, so we have for that nu bar formula will be, yes, for nu bar, that is reciprocal of wavelength. So 1 by lambda value will be here 580 nanometer. I am just have to take that value in terms of meter, minus 9 meter, and I am going to get that value will be here, that is 17.24 into, so for frequency, right, 51 point. Yes guys, so nu bar, that is 1 by lambda. So let's wait guys. Yes guys, actually that is 17.24 into 10 to the power of 5 meter, that is for nu bar. So this is the actual value for that here frequency, and for this is, that is wave number, and this is for frequency. So we have to we are actually right now calculating that is frequency and as well as that wave number. So by having these particular data here itself. Okay, so the thing is that yellow light emitted from a lamp has a wavelength of 580 nanometer. Calculate that frequency and wave number of that yellow light. So guys, yellow light is going to be traveling here and it has that wavelength corresponding 580 nanometer. So with the help of this particular wavelength, we are going to calculate here frequency and as well as that wave number for this particular yellow light. Okay, so in order to calculate those two particular parameter, we are going to have two particular formula here, that is for nu bar means for wave number, that is the reciprocal of wavelength, that is 1 by lambda, we have that. So with the help of this particular formula, we are going to calculate here a nu bar, and we got ultimately answer for that particular question will be here 17.24 into 10 to the power of 5 meter. And as well we are also calculating here, that is calculated already, that is frequency it has formula, that is C by lambda. So a nu bar which equals to, that is C, the given value means which is standard value, that is 3 into 10 to the power of 8 meter per second, and we have to substitute those two particular values in this particular equation, thereby we are going to get here corresponding value about 51.724 into 10 to the power of 13 per second. So this is the way of calculating that wave number and as well as that frequency, guys. So let's take down. So guys, we have come across with here 3 numericals, and we have you know that ultimately at the last so numericals here, but not the least as well. Okay, we'll discuss this particular formula. We'll solve this. We'll solve this particular question right now. Okay, what will be the stuff we are going to get in this particular case? Okay, so let's read that here once numerical. Calculate the wave number for the longest wavelength transition in Balmer series of atomic hydrogen. Guys, have to know that here. So you have to read that particular questions in a number of times, then only you are going to get an idea in order to solve this particular question. Okay, so right now we are going to calculate here wave number for the longest wavelength, transition in Balmer series of atomic hydrogen. Balmer series of atomic hydrogen. So guys, in this case of Balmer series, in the case of Balmer series, okay, actual the N1 value will be here 2 and N2 value will be here based on that lines. So since here we are going to calculate here wave number for the longest wavelength, means that N2 value will be here infinity. Okay, so and we got actually that RH value also here, that is RH value, suppose I just have to take here. So that is for simplification, for further simplification, that is 1 by RH value will be here 9112 angstrom. 9112 angstrom. So we should know, guys, this particular term right now, because these are very important. So without these particular data, we could not calculate here that proper, we could not get proper value for this particular question. Okay, let's have that first of all that proper formula for this particular question. So once you have to read that question again. Okay, what we are going to actually calculate here, wave number means nu bar. We are going to calculate here nu bar. Okay, by having that longest wavelength transition in Balmer series of atomic hydrogen. Okay, in this particular Balmer case, what happened, that electron has made and jumps from here a longest wavelength. Okay, so we are actually going to calculate wavelength of that longest wavelength transition in Balmer series. Longest wavelength is nothing but, guys, last line have that shortest wavelength and first line have that here longest wavelength. That's why N2 value will be here 3, not to be infinity. So we should know this particular thing. Last line, that is shortest wavelength. Okay, and in any particular series, guys, it will apply longest means first line will have here longest wavelength. Okay, so see, guys, first line having here longest wavelength and the last line having here shortest wavelength. So now the scenario used to be here, we have to calculate here longest wavelength transition in Balmer series, means first line. We are going to calculate here a wavelength for that first line. So for that first line, N1 value will be 2 in the case of Balmer series, and N2 value will be here 3. Okay, and let's have that formula, guys. That is 1 by lambda means frequency which equals to 1 by lambda, but longest wavelength means we have to take here wavelength itself, that is RH 1 by N1 square minus 1 by N2 square. Okay, So RH value I just have to put like that only 1, and N1 value what will be there guys here, 2 square, and N2 will be here 3, so 3 square. Okay, RH 1 by 4 minus 1 by 9. So RH guys have to take LCM here, 9 4s are 36. Okay, 9 1s are 9 and 4 take here, that is RH 9 minus 5 4, 9 minus 4 5 and 36 for 1 by lambda. And right now we are going to have that, we are going to get a answer for that lambda. So then we have to just you can shift that lambda to that numerator, means if you can take a reciprocal of 1 by lambda, then we are going to get here lambda itself. Okay, then this particular term is going to be like that, 36 and RH into 5. Guys, we have one particular equation, that is 1 by RH value will be here 912 angstrom. That's why 1 by RH value I am just going to substituting here 912 into 36 divided by 5 angstrom. So guys, if you are going to simplify this particular term, these particular values, we are going to get here lambda value, that is about 126.66 angstrom. So this is the stuff here. Okay, we are going to get here wavelength, and actually what we are going to calculate here, wave number. So wave number is nothing but here reciprocal of wavelength. So that's why 1 by lambda value here 126.66 angstrom, and ultimately we are going to get here value could be in terms of 7.895 into 10 to the power of 7 per meter. Suppose angstrom will be there here, 1 angstrom will be 10 to the power of minus 10 meter. So if you substitute here, and that value we are going to get in the decimal form, so we have to shift some point there, or thereby that power will be in the terms of 10 to the power of 7 per meter. So which is that answer for here, nu bar. Okay, so this is the actually guys values for that wavelength and as well as that wave number, but we are going to focus in this particular so numericals, that is only on that nu bar. Okay, because only thing is that we have to find out here wave number itself, isn't it? So guys, this is the way of simplification of this particular form, this particular question, means numericals. Okay, so guys, in this session we have been come across with here some of the numericals based on that hydrogen spectrum and spectral lines as well. Okay, so today I am going to wind up this particular class, and that next session will discuss here most important concepts like dual nature of light and matter and Higgs-Edberg uncertainty principle. So those concepts are there over, we will discuss there. Okay, so thank you and all.